This is a short supplemental video just working through an example problem of how do we sketch or select the appropriate position time graph when we only know information about the velocity and the acceleration. So let's work through our example problem. Let's discuss the meaning of the first and second derivative in these situations and how I can use that to make a rough sketch of my position of my object versus time. In our example question here, we are told that a car has a positive velocity but a negative acceleration. Sketch a position time graph that illustrates this motion. So in the first case, we're just dealing with kind of our original function here, s of t, position time, and this is a position time graph. And I don't know anything about the position and time yet, so there's nothing really to do there. What I'm going to do right away, though, is consider the first derivative. And I know that the first derivative of position time, or the first derivative of position with respect to time, is velocity. And so what does the derivative of a curve represent? Well, it represents the slope. So this is going to tell us the slope of our position curve. And what do I know about the velocity in this question? Well, it says right here that we have a positive velocity. So that means that at all pieces of our graph here, my first derivative is going to be greater than 0, and that means that I'm going to have a positive slope. So my graph is going to be increasing everywhere that I'm considering here. So that's a good piece of information to know. The next thing we need to deal with is the acceleration. So the second acceleration in this case represents the second derivative. What does second derivative tell us about our original curve? Well, it tells us the location of any inflection points if it has a 0 value, or they are possible inflection points. It also tells us about the concavity of our original curve. And in this case, we're told that we have negative acceleration. So that means that at all points on my graph here, the second derivative is going to be negative. And what does it mean if the second derivative is negative? It means that my graph is concave down. So I'm going to have, my frowny face. So using these two pieces of information, we can draw a rough sketch. And what is our function going to look like? Well, it's going to look like this. And that's kind of all we need for this question. It doesn't need a lot of detail. I just need the approximate shape. Let's quickly go back and confirm, does this meet our criteria? So we know it represents position and time. That's fine. We know the slope has to be positive everywhere. So let's test along our graph and let's see our tangent lines. Positive slope, positive slope, positive slope, positive slope. Looks good. We do notice that the slopes are less and less steep every time. That means our object is slowing down. And we expect that because we have a positive velocity, but a negative acceleration. So you can think that they are in opposition to each other. So we're moving forward, but we're kind of being pulled back. Maybe the car is coasting and just friction or wind is slowing us down. That's fine. That's what we expect. And let's confirm our concavity. Concavity should be concave down. So we could kind of continue our curve here and draw our frowny face. So concave down. Or we just see that the slope of our slopes are getting less and less steep. So concave down looks good. So we've met both criteria, positive slopes everywhere, and concave down shape. And so this is all we need. And obviously, we don't even need the blue lines. So our final answer should just look something like this, just like that first curve I drew. And that's all you need for a question like this.